Hello, hello. Welcome back to the lab. Welcome back to EEforEveryone. If you've been following along this series, you will know exactly where we are, and where that is comparators. We're doing a series that's kind of walking through some circuits 1, circuits 2, kind of level college concepts, and sharing that with you. Thank you so much for being here. This next step of the journey is comparators. Oh boy. Yep, we're talking about comparators. So, specifically, today we are talking about ideal comparators. What is a comparator? Well, a comparator is a pretty simple device. Usually the circuit model that we would draw is something like this. And what does it do? Well, that's pretty simple, actually. How do we want to draw this? Let's just start with the bullet points. We'll say for a regular comparator, when plus is greater than minus, those are the positive and negative. Oh, wow. Those air quotes are not working. You know what I mean? When positive is greater than negative input, the output equals high, like a logical high. Whoops. When negative is greater than positive, output is low. It's pretty much as simple as that. If you're familiar with op amps, this should not be very surprising. It's kind of like an op amp, except for it's designed to be very extreme. It's designed to snap to one or the other, and it really isn't designed to be used in the middle ground. So how exactly do we use one of these devices? Well, there's a couple things that we need to hammer out, and specifically around this ideal assumption. What does that mean? Well, for an ideal comparator, let's just think about this for a moment. For an ideal comparator, there are some nuances. Sorry, for a real comparator, there are some nuances, and that is specifically, there is a VCC voltage. There is we'll call this VSS or ground voltage. That might not be exactly 0 volts, or let's say 5 volts or 3.3. It might be somewhere kind of in the middle. And this output voltage might not be exactly VCC or VSS. It might be kind of in the middle because of some non-ideal parameters inside the part. And basically what I'm saying is, no, we're not thinking about that right now. We're not thinking about that right now. So we're going to be making a lot of assumptions. Okay, so when these are ideal devices, what does that mean? It means you're going to have some assumptions. What are we going to assume? We're going to assume that V out equals V in. We're going to assume there's no internal losses in the part, and that a logic 1 is whatever voltage is applied to the part. We are going to assume that there are no input bias currents. And these are currents that flow into the comparator. And these can actually be in either direction. And these vary with temperature. These vary with component tolerance. But we're going to assume they're all 0, no current. They're usually pretty small. We're also going to assume that there is no input offset voltage. And that's the voltage right there. So normally it would trigger right at that level, right? It would trigger, so right, you got 5, let's say you got 2.4 volts, and you got something that's kind of slowly coming up, and you'd expect right at that threshold, it would go kapling. Realistically, it probably needs to exceed that threshold by a couple millivolts. Perhaps there's some built-in hysteresis. Perhaps there's not. Could have some oscillation. Could be a little ugly. So we're just going to assume that's, there's no oscillation and there's no input offset voltage. Okay. Oops. All right. So IB1 equals IB2, so it's input bias equals 0 microamps. Also 0 amps. 0 every current unit. And we're going to assume that input, the input offset is 0 volts. There we go. Let's see, what else do we need to assume? So we've covered the assumptions on the output. We've covered some assumptions on the input. No oscillations, of course. No oscillations. And in this case, we're going to assume it's a push-pull comparator. Actually, you know what? Let's not do that. Let's dive into that. Let's dive into that in a moment. Okay. No oscillations, no hysteresis. That's probably good enough. I'm sure I'm missing something, but that's probably good enough. Let's dive into what I just alluded to. That is output configurations. Okay, there are 3 main types of outputs. There is push, pull, there is open collector. Those are certainly the most common. You could also have an open emitter, but that would be kind of weird. You know what? Let's just pretend there's only 2. Push-pull, open collector. Certainly the most common by a long shot. So, how do we think about a push-pull comparator? Logically, we've got our 2 inputs. We've got kind of this logic cloud of analog, digital, kind of this analog to digital conversion, a slew rate nonsense, and then this comes out, and what you basically have is an H bridge. That is the output of a push-pull comparator, where this is V in, and that's your ground reference. And that is a push-pull comparator. For an open collector comparator, what you would have is you'd have your positive and your negative. It would go into your logic cloud of circuitry, and it would come out to only a low side transistor. So this would be our output. What is the critical difference? Okay, yeah, let's talk about that. So let's draw a little graph here. And so we're going to define Vn as V plus minus V minus. So basically, a negative voltage should have a negative output. A positive voltage should have a positive output. That's what we're going to draw. And we're going to draw a graph of, Vn over time. So this is time in this axis, and this is Vn in this axis. And we're going to call this 0, 0. Okay. And we're going to start with some negative voltage and come up and maybe do some of that. Okay. And we're going to do that same thing over here. Wow, that is really not a straight axis. I think I can do better than that. There we go. Okay. Same definition of V in. And we're going to do that same kind of shape. Okay. What is happening on the output? For our push-pull comparator, remember push-pull's on the left. What we're going to see for V out, and let's see if I can change color. Can I change color? Oh, you better believe we can. All right. So in the output, we would see this. When we have a negative V in, we would see 0 volts, and when it's positive, kapoing, it would pop up to V in, and it would stay there. Beautiful. That's approximately how a comparator would function. Never mind that whole negative slope thing. Okay, I'm not perfect. And then if we go ahead and look at the open collector, what we would see is we would see 0 volts clamped to 0 volts. And then we would see this big box of, I have no idea. It lets go. It stops holding on. We don't know. And what do I mean by that? What I mean by that is, let's say that we were to take this output and we were to add a resistor that goes up to VDD. Well, if there's no other loads and the output isn't being pulled to ground, then yeah, it would go up to VDD. But let's say this was 3 volts or 5 volts or an I2C bus, or who knows what you're connecting that to. That could be a little weird. Why is this important? Why does output configuration matter? Why do we care? Well, let's do a circuit analysis example with an ideal comparator. We're going to have a sinusoidal source over here with a magnitude of 3 volts, 1K resistor, 1K resistor, and V out over here, positive, negative, positive terminal there. Negative terminal is fixed at 1.5 volts. That's the positive terminal. V in is 5 volts. So basically, when this terminal is above this terminal, V out will be equal to 5 volts for the push-pull comparator. Speaking of, let's go ahead and draw these waveforms. Let's get some grid lines going. That's the good stuff. Okay, so this is V, this is time. And we're going to draw V in black. Okay. We've got 4 grid lines. There we go. So this is 3 volts, negative 3, that's 0. And then that's 6 volts up there. Excellent. That's V in. Then we're going to draw V plus, push-pull. Now in this case, when everything's booting, we're going to assume that it is all starting from 0 volts for the sinusoid, and we're going to assume that we're snapping immediately to 1.5 volts on the negative input. And that means that V minus is just a constant 1.5 volts. I think I can do better than that. Oh, there we go. Okay, constant 1.5 volts. V out ends up being halfway between whatever the output state is and whatever this is. And what I'm going to demonstrate here is that for a push-pull comparator versus a open collector comparator, these are going to look a little different. There we go. These are going to look a little different between the open collector and the push-pull comparator. And so then we're going to call this VV plus open collector. Beautiful. All right, how's this going to look? Actually, I think that's going to be super in the way. So we're going to put this over here. V plus OC. Excellent. So which one do we want to start with? Open collector? Okay, we'll start with open collector. So that means that whenever the input is less, it is clamped to ground. So that means... I screwed this up again. This is the second take. Come on now. Don't even. Okay, I'm not going to totally start over. I'm going to take you along for the ride. This is going to be 1.0 volts. 1.00 volts. Beautiful. This is going to be V minus. It's going to be right there. Perfection. Don't even worry about it. 1 volt. All right, so we're going to do V plus OC, and we're going to do V plus push pull. Okay. For the open collector comparator, we're starting this off with clamp to ground. And what we're going to see for this waveform is that it goes up with what would be a peak voltage of 1.5 volts. I'm just going to dash that. And we're going to draw this solid up to there. Okay. But what do we see where I've dashed this? Once we hit that threshold, what's happening? Well, in that case, for the open collector comparator, when this stops clamping to ground, we essentially remove this 1K resistor. And the waveform would snap up to, what is that? Vin. So basically we'd see this waveform have a discontinuity, jump up to Vin, and ride this wave all the way back down here, where it would then jump back down to being divided by 2. And it would finish out its life. And then, of course, it would just be, assuming we didn't blow anything up, it would be half the waveform on the other side. That looks pretty interesting. Wow. Okay. But for the push-pull comparator, what is the difference? Well, the difference is that when we switch states, when that comparator switches states, it will no longer jump from half the magnitude to 1 times the magnitude. It's going to jump from 1/2 the magnitude to the average of V out and this voltage. So that basically means that if we sketch 5 volts in here, what do we got? We got 5 volts. I can do a better dash than that. We're going to pretend that's 5 volts. That's a little off grid. We're going to jump to halfway between here. Basically, right about there. So this is going to jump up and stop right about there. Then it's going to finish riding that wave. And now this is going to get really hard to do because now I need to average the positive and negative waveform. -3, +5. What's my lowest point? 5 minus 3 divided by 2. Wait. 5 minus 3 is 2. Divided by 2 is 1. So we're basically going to come down, and at that very lowest point of the sine wave, we're going to scrape, but I'm going to say we don't quite cross it. And we don't change state again. We're equal. We're not less than. It doesn't change state. That's going to be my assumption. And so the difference between the push-pull waveform that push-pull waveform, what do we got here? Oh, I love that color. Nice, great color. The difference between this push-pull waveform and the open collector waveform is pretty extreme. One turns on and latches forever, and the other one turns off and turns off every cycle. So that's very, very different. Not to mention, the output waveform looks very, very different, since the output waveform for the push-pull would look like this. That's a pretty clean output waveform. And of course, for the open collector version, it would look like this. That's pretty strange. Pretty strange. Okay, that was an ideal comparator. Hopefully you were able to follow that example. Yeah? Maybe? Yeah? Maybe that was a little bit too much. Maybe that was a little bit too much to go from DC steady state analysis to AC circuits. But I needed to get some voltage transients in there to really express the difference between a push-pull and an open collector comparator. It's really not that complex. What we're really looking at is the difference between an open collector output stage and a push-pull output stage. I just want to take a moment to say that if you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we're going to translate this into real comparators, no longer ideal. That is going to be an adventure. Make sure you don't miss it. I can't wait. If you'd like to support the channel, don't forget to hit that like button, get subscribed, and consider checking out the Patreon page linked in the description. It really helps us out a lot. Thank you to everyone who's decided to back us on Patreon. It really helps a lot. I appreciate you. Most of all, I hope that you learned something great, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye.